Okay, I think we are going now. All right, so complex zeros of polynomials. Let's start with this whole complex number thing. Make sure we're still good with those. All right, so as you've seen before, complex numbers are numbers that kind of come in two pieces. They have a real part and an imaginary part. And they're written like this. A plus bi. And the A is the real part. And the I is the imaginary part. All right, now, imaginary numbers. Does anybody remember where those come from? How do we end up with imaginary numbers? Yeah. Go ahead. Square rooting negative numbers. Right. So, like if I tried to do the square root of -4, okay, normally we would say, oh, you can't do that, right? You can't take the square root of a negative number. In fact, when we were talking about domains earlier in this class, we talked about that a little bit. Square roots are one of those things we had to be careful of. You can't square root a negative number. Well, the reason that we were saying that was because we were working within the real number system. So when we talk about a domain of a function, we're talking about just real numbers. What's the domain? If I had asked what's the domain involving imaginary numbers, we could actually expand that out a little bit, but we're not going to go there with that. In any event, the square root of -4, square root of 4 is 2, but the square root of -4 then would be 2i. And when you break it down, really it all stems from the square root of -1, which is just I. So that's kind of the definition of I. Like, where does I come from in this whole thing? Well, it's the square root of -1. So we're going to look at that. When we come up with some of these complex roots, we're going to be dealing with square roots of negative numbers and pulling them out that way. Okay. I think my Algebra 2 class, if you had me last year, I talked about this a little bit, where the name imaginary comes from, because it's really confusing to a lot of students. Like, why do we call them imaginary numbers? Because they obviously exist. We use them, right? Well, the reason they're called imaginary is because the mathematicians who are first looking at this stuff, they didn't know if they were real or not. They were just theorizing that they were real. They thought maybe they were. So in all of their proofs, all of their papers that they were writing and submitting to, professors and stuff like that, they kept referring to them as imaginary numbers because they still weren't sure. Well, later on, it was proven that yes, they do exist, and we can work with them and use them and all of that. But the name imaginary had been stuck to them for like 100 years, and so people just kept referring to them as imaginary because it was like the common thing to call them, because that's what people were used to calling them. And so as time went on, we still call them imaginary numbers, even though they have uses and that sort of thing, but we just refer to them imaginary even though they're real. So it gets kind of confusing in the whole verbiage thing. Yeah?
What even proves that a number does or does not exist?
That's a very complicated question. I cannot answer that, but you can. All right. Anyway, that being said, let's move on. So that's a complex number. So we're going to have roots that will come out as being complex. Okay. So the fundamental theorem of algebra takes this idea and what we talked about yesterday and puts it together. If we allow ourselves to use complex numbers, not just real numbers, but complex numbers too, then the degree of a function, or the degree of a polynomial, is equal to the number of the roots that you'll have. Basically just that statement. A polynomial of degree n has n complex roots. Now remember when we were talking about real numbers? Okay, real zeros. We said that a polynomial's degree was at most how many it could have, right? Remember that polynomial investigation we were talking x-intercepts? We said the degree was always the maximum number of x-intercepts it could have. So it might have that many, but it might have less, right? Well, if we allow ourselves to look at complex numbers, which is imaginary, real, all of it together, then the degree is always exactly the same. Okay? Those x-intercepts are only the real solutions. It's not all the imaginary ones. So you're only getting part of the story there. But if you allow complex numbers in the game, then the degree and the number of roots is exactly the same. Okay? So what we can do with that then is, if we have some sort of a function that might involve some imaginaries, we can actually we will know how many roots we should have, and then we can go in search of all of them. So, give you an example. Let's say we've got x to the third minus 5x squared plus 2x minus 10. All right, and so just so we can kind of get the ball rolling here, I'm going to let you know that x equals 5 is a root. Okay, so we've got one of them. How many complex roots should this thing have total? 3. How many of them do I know right now? 1. Even though this is just x equals 5, that's technically a complex number. A complex number is imaginary, real, all of it. Okay, it's all of those. So this is one of our complex roots. We know that we have 2 more to go then, right? So let's do like we did yesterday. Let's do a little synthetic division. We'll take out the one that we know, and then see what we got left over. So bring down the 1. 5 times 1 is 5. Negative 5 plus 5 is 0. 5 times 0 is 0. 2 plus 0 is 2. 5 times 2 is 10. So, yep, that works. So, this is what we've got left over to work with now. So that is x squared plus 2. And in that little polynomial are the 2 other roots that we want to find. Yeah?
How did you know 5 was a root?
I just told you that. Like I said, for this one, just to get the ball rolling. Otherwise, what you'd have to do is the rational root test. Factors of 10 divided by factors of 1, and then like test them all out. But to save some time, I said, okay, I'm telling you, 5 works.
Yeah, but how did you know that?
How did I know that? Because I've done this problem before, and I know the answer. So what we got left over, x squared plus 2. Remember, we're trying to solve that yet, right? We're looking for zeros. So where is it equal to 0? That's going to help us get the roots. Now, as soon as you start to try and solve this, you're going to see the problem, at least doing it the old way that we were looking at it. If I subtract 2 to the other side, x squared equals negative 2. Well, how do we solve an equation with x squared in it like that? Square root both sides. And there's your imaginary number coming into play, right? As soon as you square root both sides of that, then you're square rooting a negative number. Okay? So, looking at real zeros, we'd say, can't do that, done. There's only the 1, just the 5. But if we're talking about complex, we can keep going with this then. So x equals the square root, or plus or minus the square root of negative 2. Now, written as an imaginary number, that would be x equals plus or minus the square root of 2i. Okay, because it's the square root of negative 2, we get rid of the negative, and that's the I, because the square root of negative 1 is I. All right, so we've got 1 real root, 2 imaginary roots, 3 complex roots altogether. Okay? And oftentimes they're going to be asked to write the solutions as complex numbers. Okay? So, I've got this one and these two. I'm going to write them as complex numbers for my answer. So I'd have x equals 5 plus 0i. Okay, that's this one. There's a real part but no imaginary part on that one. And then these guys down here, there's 2 of these, and those are, they have no real part, just an imaginary part to them. So x equals 0 plus the square root of 2i, and x equals 0 minus the square root of 2i. So degree of 3, we are able to find all 3 complex roots for that one. Okay? That's what that fundamental theorem of algebra says. Whatever the degree is, that's how many you should have when you're done. Yeah?
We have to write them out like that every time, even if it's 0i.
If the problem might ask you to write it in the form a plus bi, and if you see that, then yes. If no, then just leave them the way you had them. That's fine. Usually I don't care, but if the directions state it that way, then you're going to have to probably follow that. So, okay. So let's see if we can go the other direction with it, because I said that's kind of where I want to start before we get into doing more of this type of a thing. So if I give you some zeros that are complex numbers, can we build a function from that? So let's say f of x has zeros, x equals 2, and then let's do 3 plus I and 3 minus I. Okay, so I've got 2 complex numbers here that are roots, and I've made them so that they have both a real and an imaginary part. And then we're going to see if we can put all of this together into a function. So we're going to write f of x in standard form. So if you see that, write it in standard form, that means you're going to have to multiply it all out. So the steps in this process are going to be take the zeros, make them factors, take those factors, multiply them all together. Be careful with the imaginary pieces of it as you do that. Okay? That's where it can get a little tricky. Alright, so f of x. Each of these I'm going to turn into a factor. What's the factor that goes with x equals 2? X minus 2. Okay. The factor that goes with 3 plus I. Nope, we're just talking the factor. So it would be x. It's always x minus whatever the root is, right? And that works for complex numbers as well. So it's x minus 3 plus I. Like that. And then the other one, x minus 3 minus I. Okay, so always kind of stick to that formula. X minus the root. X minus the root every time. Now, you can simplify these up a little bit. You got to distribute the negative each time. Before you start to multiply, I would definitely do that. So x minus 2, this is x minus 3 minus I, and this one would become x minus 3 plus I. And then we're just going to start multiplying everything to everything. Okay? Now my suggestion to you before you start going after that, take care of the ones that have the imaginary numbers in them first. Because if you're doing your math correct, you should eliminate all of the i's from the equation by doing that. And I'll show you that process here next. After you have that done, then take that answer and multiply it by x minus 2. It should be a lot less work to do. Okay, so I'm going to leave this one alone. And let's just be very careful. Every part of this multiplies to every part of that. Okay, so x times x, x squared, x times negative 3, x times I, and then go to negative 3. So negative 3 times x, negative 3 times negative 3, negative 3 times I, negative I times x, negative I times negative 3, and negative I times I. Okay, so it's all of that. All right, there should be, like I said, a lot of cancellation happening if you've done all of your multiplying correct. So do you guys see any of it? What should be canceling in there? Pretty much everything with an I in it, except for the I squared. Yeah, but that will take care of a different way. I'll show you. So yeah, so there's this plus ix minus ix, minus 3i plus 3i. All that's gone. So we got x squared minus 3x plus 9 minus I squared. Broken it down to that. So the 3x's can go together. So x squared minus 6x plus 9. Now what about this I squared? Yeah. Right. Because remember, I is the square root of negative 1, right? So I squared should just be negative 1. Get rid of the square root symbol, right? So I can take that and turn it into a negative 1, but be careful because it's negative I squared. So it'd be a positive 1, right? So that plus 1. So what we really have here is x squared times x squared, or x minus 2 times x squared minus 6x plus 10. So like I mentioned, if you've done your multiplication correctly, there shouldn't be any i's left. And now it's another just be careful, multiply, multiply, multiply type thing. So x times x squared is x to the third, x times negative 6x, x times 10, negative 2 times x squared, negative 2 times negative 6x, and negative 2 times 10. And do a little combining like terms. We'll get our final equation for f of x here. So x cubed minus 8x squared plus 22x minus 20. So apparently this polynomial has the roots 2, 3 plus I, and 3 minus I. That's what we did. We used the roots to go back the other way. Is this a little tedious? Yeah. A little bit with all that multiplying. Is it easy to make a mistake? Yeah. So you got to be careful of that too. More often than not, though, we're not going to go this direction. We're going to go the other direction with it. But I like doing these kind of problems as part of the notes, though, just because it helps you to see the connection between the zeros and the equation itself. Okay, whatever those zeros are, real or complex, you multiply them together as factors, and that gets you the equation for the polynomial from whence they came. So it's a good connection that way. So one thing that maybe you noticed about this one is those two complex roots that I gave you. What do you notice about those two? Are they similar in any way? Yeah. Right. They're alike, except one is 3 plus I and the other one's 3 minus I. There's a special name for that. It's called conjugates. Okay. If you have two terms that are exactly the same, except one's being added and one's being subtracted. Those are called conjugates. So these are called complex conjugates. And what ends up happening with every one of these problems that end up having imaginary solutions or complex numbers that are in there with imaginary parts, they always come in these conjugate pairs. There's a plus and there's a minus. Even look at the one that we did before it. Take a look at the two answers that had imaginary parts on them. Aren't those conjugates technically? It's with 0, but it's still a conjugate. 0 plus the square root of 2i and 0 minus the square root of 2i. They came together again as a conjugate pair. Okay? And that's another theorem that we're going to look at here involving complex roots. You never have a complex root with an imaginary part by itself. It's always going to have its conjugate pair coming with it every time. Okay? So I'm going to jot that down. And we're going to use that fact to help us. Because if I give you a complex root, you can always tell me another one right away. Because you know the conjugate needs to be there. All right, so complex zeros always come in conjugate pairs. A plus bi and a minus bi. So what that allows you to do is, if you have some polynomial, let's say we're going the other direction now. I'm going to start with the equation, and we're going to see if we can pull out what the roots are. So if like that other one, I told you x minus 5 is a root. Just going to give you that one to start with, okay? So if the one I just give you is a complex number, then you can actually say, oh, all right, I got another one. I got a second one I can use too. So let's see, what's one I can give you? Find one I can steal that works well here. Okay. Okay, so we're going to look at that one. And let's say, for this particular one, x equals I is a root. So there's your freebie. We know I is a root. So if I know that I is a root, or technically 0 plus I is a root, what's another root that must be with this equation as well? Yeah. So the conjugate of that, 0 minus I, must also be a root. because of that complex conjugate zeros idea. All right. So this will be the last thing that we do today. So what we're going to do then is we're going to start the process of, if I know a complex root, how do I then go through synthetic division like we did with real numbers and find the rest of my zeros? Okay? The process is exactly the same, except for when you have imaginary numbers in your synthetic division, you have to be careful about the properties of those and using them the right way. And we'll come across some of those as we go here. So, I know that x equals I is a root. So, just like we did before, instead of a number or a real number going in the box, now I'm going to put I in the box. Take all the coefficients off my polynomial. And work through a synthetic division. Now with these, if you haven't yet, you might want to do this before we get started, but you're going to want to kind of space these out a little bit more than you normally do, because we're going to have some complex numbers in there. All right, so first things first, bring down the 1. I times 1. Just I. Okay, then, what do we do down the columns? We have to add them together, so this is 3 plus I. Like that. Okay, like I said, you're going to need a little more space. And then, what do we do? Times by I. Okay, I'm going to go to the board here, and I'm going to do that. You might be able to start doing this in your head in a little bit, but this first one, I'm going to write them over here on the board so you can see it written out a little bit. But if I do I multiplied by 3 plus I get 3I plus I squared. Right? If I distribute the I into there. But what is I squared? Negative 1. So what I actually have is negative 1 plus 3I. Okay? Now if you need to go off into the margin of your paper and write that out every time, that's totally fine. Please make sure you're doing it the right way. But after a while, you might be able to start doing that in your head. So negative 1 plus 3I, though, is what we get when we multiply those together. Okay, so then, again, add down the column. Okay, like terms, what do we get? Mm-hmm. And then multiply I times that. So if I distribute that I, I've got negative 4I plus 3I squared. And again, I squared is negative 1, so it's negative 3 minus 4I. Okay, add up that column. What do I got? I think I heard somebody say negative 4I. That's right. And then if we multiply again, I times negative 4I is negative 4I squared, which is positive 4. So even though my answer is a bunch of complex numbers, it did what it was supposed to do, though, right? Remainder of 0. Okay? That's what we're supposed to get when we have a root. Remainder of 0. And even though it was complex, that did do that. Okay. So, I've got that one out. And this would be the coefficients of my polynomial. Please don't write it out with those coefficients. It's going to look really nasty. Because I got one more synthetic division to do right away, right? What's the other root I know that I have? Negative I. So I'm going to repeat the process with this using negative I. And this one, if you've done the first one correctly, this one turns out way easier every time. It goes so much faster. But we got to copy these coefficients down onto this one. Okay, bring down the 1. Negative I times 1. Negative I. Add them up. 3. Negative I times 3. Add them up. Negative 4. Negative I times negative 4. 4I. And like we're supposed to get, remainder is 0. And if you've done your math correct, the answer to this one should have no more i's, because we've taken care of all of our imaginary roots, right? We took care of both of those conjugates. They're both gone, so what's left? We should be looking for some real zeros now. And what we have is x squared plus 3x minus 4, which is factorable. I can find the rest of those roots by factoring that thing. What adds to 3 but multiplies to negative 4? Okay, so I've got my other two roots. X equals 4. I'm sorry, negative 4. And x equals positive 1. Okay? So, negative 4, 1, I, negative I. How many roots do I have? 4. What's the degree? 4. Degree is 4. Should have 4 complex roots. Got them. All 4 of them. Okay? Tomorrow in class, you're going to be doing mostly this kind of stuff, practicing this. Okay? Using those complex roots to get more complex roots, and then to get the rest using your synthetic divisions. All right, we'll stop there for today.